Okay, so let's get started. Hey guys, first of all, let me thank the organizers and in particular to Tommy for this very kind invitation to this unusual online conference. So let me now share my screen. Okay, so we'll talk about the dark matter production, in particular dark matter production in the early universe via this ultraviolet freezing, and how the production before the reheating can boost this production, right? So it's based in these two papers made in collaboration with Maria Dutra, Jan Nombrini, Keith Olive, Marco Pelosa, and Matthias Pierre. The first one, Fatemeh Elai, Carlos Maldonado, and Jameson Wing. And in particular, this one that appears on the internet, on the archive early this week, done in collaboration with Javier Rubio and Hardy Vermeer. So I'm Nicolás Bernal from Universidad de Narino in Bogotá, Colombia. Okay. Okay, so I don't think I have to convince you about the existence of dark matter. So just let me tell you a couple of things. In particular, you know that there are several observations that indicate the existence of this non-luminous matter, of this dark matter, as a missing gravitational force, and at very different scales. In particular, we have some hints at the scales of galaxies, but also at the scales of clusters of galaxies, so the megaparsecs or so, and even the biggest scales of the universe, so the cosmological scales with this inhomogeneities of the CMB that can be very well explained the framework of this lambda CDM model, where the cold dark matter plays a fundamental role. So I have to show you this plot. So in this is an arepa, so a Colombian arepa, and if this corresponds to the 100% corresponds to the matter and energy budget of the universe, you know that only 5% or so corresponds to the baryonic matter, so the standard model basically, whereas 25%, so 5 times more, is in the form of this dark matter that we'll focus on, right? So we are kind of convinced that dark matter is there. However, we don't know what it is. We know that it has some properties. For instance, it's neutral, it's massive, it has some weak interaction with the standard model, weak in a very broad sense. And this dark matter is stable, or at least long-lived, with a lifetime of the order or higher of the age. So we know that dark matter needs new physics beyond the standard model, and that's why it's so exciting, this subject. Now, the first question that we can ask is, how was dark matter produced in the early universe? So we don't know. However, we have several mechanisms, and in particular, I think our favorite one corresponds to the WIMP paradigm, where the dark matter is a weakly interacting massive particle. So in this paradigm, so the key point is that dark matter reaches chemical equilibrium with the standard model in the early universe. So that means that, for instance, in this plot, I'm showing you the dark matter yield. So and this corresponds to the dark matter number density normalized by the entropy density as a function of the inverse of the temperature, of standard model temperature, photon temperature, if you want. So time is flowing from left to right. This dashed line here corresponds to the equilibrium density, and these 3 lines correspond to the dark matter density, so dark matter abundance, that is tracking the early universe, its equilibrium density, and at some point we say that it freezes out. That means that the equilibrium is broken, and it reaches a plateau, and that's how the dark matter relic abundance is generated, the dark matter relic abundance that we measure today. So in order to keep track of the evolution of the dark matter relic density, we have to solve this kind of Boltzmann equations. So where n corresponds to the dark matter number density, t is time. This term here corresponds to the dilution due to the expansion of the universe, where h is the Hubble expansion rate. And these terms here in the right-hand side of the equation correspond to the interaction. So basically, to the annihilation rate. So that a couple of dark matter particles annihilate into standard model degree of freedom. And this term here corresponds to the dark matter production. So standard model annihilating into dark matter particles. And this term here, sigma V, corresponds to the thermally average annihilation or production cross-section, right? So this is the kind of Boltzmann equation that one has to solve in order to keep track of the dark matter abundance. So this typically rewritten in this shape, where Y, capital Y, corresponds to dark matter yield. So dark matter number density normalized by the entropy density, and X is just dark matter mass over the temperature, right? So we can solve this kind of thing. So the weak paradigm means that the dark matter reaches chemical equilibrium, and in order to have that, or in order to reproduce the observed dark matter abundance, this sigma V, so this rate, if you want, has to be of the order of few times 10 to the minus 26 cubic centimeters per second, right? Kind of independent of the dark matter mass. And the temperature where this dark matter goes out of chemical equilibrium is basically the dark matter mass over a factor of few, 20, 25, whatever, right? So you have these conditions, you can guarantee that the dark matter is produced via the Wien paradigm. And one point I want to stress is that it's completely independent from initial conditions. And when I say initial conditions, for instance, I'm thinking about the dynamics of the reheating, for instance, reheating temperature, inflation, right? All this. So that's the Wien paradigm, and I think it's our favorite one. However, we know that there have been a big worldwide effort to detect this kind of dark matter, Wien dark matter, using a multi-channel and multi-messenger approach. However, we have failed, so there's no compelling detection so far. So that could indicate that we can go, or that we should go beyond this very simple Wien paradigm. And there are several options. One of them is to think about non-thermal production, for instance, with the FIMP paradigm. So in this paradigm, the dark matter is feebly interacting with massive particles. And what we have to do is basically to solve the same kind of Boltzmann equation. However, we're assuming that the interaction rate is very small. And that means that the dark matter will never reach chemical equilibrium with the standard model. So that means we will produce dark matter, but dark matter will basically never efficiently annihilate. So that's why we can get rid of this term as a first approximation. So the annihilation term will have only the production term of dark matter. So as I told you, what we want is this sigma V, so the interaction rate to be very small, so dark matter never reaches chemical equilibrium with the standard model. And that can be guaranteed if we have renormalizable operators, so connecting the two sectors with very small coupling. And the coupling between, say, the dark matter and the visible sector could be of the order of 10 to the minus 10 or so, 10 to the minus 11. So very small numbers, so that we can say that they are unnaturally small. However, in several models or in models, this number could be at least technically natural, right? So dark matter never reaches equilibrium because their interaction rate is small, and that's due to the very small coupling, order 10 to the minus 10, 11 or so. And in this free paradigm, and this is the infrared free paradigm, the bulk of the dark matter is produced at small scale, meaning electroweak scale, if you want, when the temperature is of the order of the dark matter mass or of the order of the mediator mass, right? So it's infrared, but infrared, meaning electroweak or so. So if you solve this kind of Boltzmann equation, what you will see is that the dark matter abundance or the dark matter yield slowly increases, and at some point it reaches the plateau. We say that the dark matter freezes in, right? And the maximum of the production typically happens, I told you, when the temperature of the plasma is of the order of the masses of the mass of the dark matter, of the mass of the mediator. So there's a mild dependence from initial conditions, and in particular, it's typically assumed that the if you want the initial dark matter density is zero or is very small. However, yes, I want to emphasize that there's an assumption, right? That the dark matter abundance at early times, so at very high temperatures, is very small, right? So that's the thin paradigm, the infrared thin paradigm. If there's infrared, that means that there's also an ultraviolet. So the UV thin paradigm, again, is the same logic. We want dark matter. We don't want the dark matter to reach chemical equilibrium. We want it to be always out of chemical equilibrium along the history of the universe. And the difference here when you have UV freezing is that it's reached by the use of non-renormalizable operators, right? So typically, so this sigma v, this annihilation cross-section, we assume that it comes from a non-renormalizable operator. And in particular, we can parameterize this with this function. So sigma v, we can say that goes like Tn. So T is the temperature, again, the photon temperature power n over lambda 2 plus n, where lambda corresponds to, if you want to scale of new physics, or if you want, it's a proxy of the mediator mass. So we want it to come from a non-renormalizable operator, so the operator of dimension 5 or higher. So we want this lambda, so this scale of new physics, to be higher than the reheating temperature. And in this case, the bulk of the dark matter abundance will be reached when the temperature is of the order of the reheat temperature. So this production will, the peak of this production will not take place at the electroweak scale, but more at the reheating scale. So if you solve the Boltzmann equation, so y as a function of t now, you will find this kind of evolution. So you start with zero, for instance, with a very small abundance, and you very fast reach plateau. And this and the bulk of this production happens when the temperature is of the order of the highest temperatures of the universe, meaning at least in this approximation, the reheat temperature, right? So that's why it's called UV, because the bulk of the dark matter abundance happens at T reheating, right? And here I want to emphasize that there's a strong dependence from the initial conditions. In particular, there's a strong dependence on the reheating temperature. So here I'm showing you, for instance, so we can solve the Boltzmann equation, and you can see how that the yield, so the dark matter abundance, has a strong dependence on T reheat. So it depends, it scales like T reheat over n plus 1, where n, remember, is the temperature dependence of this sigma v. So what you have to have is, once you have fixed your particle physics parameters, for instance, the mass, the scale lambda, so you can always tune the reheating temperature in order to reproduce the observed dark matter abundance. So these 4 lines correspond to 4 different values of n, 2, 4, 6, and 8. And you can see that for each, okay, for a given dark matter mass of 100 GeVs, and for a given for a given scale, capital lambda, you can always tune T reheat in order to reproduce the observed dark matter abundance. And this T reheat spans over several orders of magnitude. You can see from 1 to 13, to 13 GeVs, right? So now let me do a small comment about this parameterization. I don't know how, if you guys are used to this, but this sigma v parameterization this way, so like T power n over lambda 2 plus n is something that is kind of standard, of easy, relatively easy to find. So for instance, suppose we have the dark matter, the standard model connected to the dark matter via the F channel exchange of a mediator, right? So if this mediator is heavy, automatically, and when I say heavy, means heavier than the reheating temperature, this will automatically guarantee that the sigma v will go as T squared. So suppose G is the coupling, G and G. So you have that this cross section will scale at G power 4 times T squared over M4, right? So you have a heavy mediator, you automatically have like a T square dependence of sigma v. the same will happen if instead of a heavy mediator, you have very suppressed couplings. So because, I know you can have an effective coupling here because you have heavy particles flowing the vertex or whatever. So in that case, the same thing happens. You will have a suppression of the couplings of lambda 4. And in that case, you will have a t-square gain, again a t-square dependence on the sigma v. But you can also have as a heavy mediator and a suppression. And in this case, you will have a T6 behavior of this annihilation cross-section. So a small comment just to motivate the choice of this kind of parametrization of the annihilation cross-section, right? Now, let's go back to the reheater, in particular to this approximation of instantaneous reheating. So here I'm showing you two plots, one of a temperature and a function of A, and A is the scale factor, and rho is the standard model energy density as a function, again, of the scale factor. So in this approximation of the instantaneous reheating of the universe, instantaneous reheating of the universe means the instantaneous decay of the inflaton. So the idea that before reheating, you have basically the inflaton roaming around, and it decays instantaneously, and after that, the scales like 1 over A, because you assume that the entropy is conserved, and rho scales like t power 4. That means that A to the minus 4, right? Rho is the standard model energy density, because we're assuming that, as I told you, S standard model entropy density is squared, and also Hubble will go like t squared, because the energy density is dominated by radiation, right? By standard model radiation. So, and yes, these are pretty much the common law of the particle physics community and of the evolution of the universe, basically. So I'm exaggerating a bit, but not too much, actually. So let's take one step forward and go beyond this instantaneous reheating approximation. So in the non-instantaneous reheating approximation, we can take the decay of the inflaton into standard model radiation as a continuous process. So if you want to keep track of the evolution of the energy density of radiation and inflaton, phi is inflaton, we have to solve this kind of open equation, where omega here corresponds to the effective equation of state of the inflaton after inflation. So omega, if you want to take omega to be 0, it will be like a reheating of the when the inflaton is oscillating in a quadratic potential. So take omega equal to 0. And so, okay, and we have, so we assume that the inflaton is decaying into standard model radiation. So we have this kind of term where gamma corresponds to the decay width on the inflaton, with a minus sign because it's decaying, and here with a plus sign because the inflaton is pumping energy into radiation, right? So these are the equations for the Boltzmann equation for the background. So the inflaton decay width, like I told you, is gamma, is this number gamma, and it gives you the reheating temperature, because after all, you can say that the reheating temperature corresponds to the moment where Hubble expansion rate is equal to the decay width, right? And also for the Hubble expansion rate, you have actually two components or two contributions, one coming from the inflaton energy density and the other from the radiation energy density, right? So at this point, we have like 3 or 2, if you want, 3 parameters, the decay width of the inflaton, so an initial expansion, Hubble expansion rate, so if you want the scale of inflation, and omega, which is the effective equation of state of the inflaton after inflation. If you want to take this omega to be 0, we took a general omega just to understand what's the role of these parameters. So this is something which is kind of well known, actually since '98. It was pointed out by Schum, Kolb, and Ryotto that actually away from the instantaneous decay of the inflaton, the standard model thermal bath can reach a temperature T max, the maximum temperature of the universe, which is much higher than T reheat, and that's only due to the non-sudden decay of the inflaton. So, and that means that before reheating, so after reheating, the energy density of radiation will scale at 8 to the minus 4, as we know. But before that, it will scale like this, 8 to the minus 3/2 of 1 plus omega, right? Because we are having the inflaton, which is decaying into radiation, so it's pumping really energy into the standard model. And also before reheating, so after reheating, sorry, T goes like 1 over A as expected, but before that, the temperature goes like A plus scale factor minus 3/8 of 1 plus omega, right? So we have like this non-standard evolution of temperature and of rho, so energy density of the inflaton in blue and radiation in black. And so we have 3 parameters that can be reparameterized as T max, T reheat, and omega that we put to 0 here, right? So what we want to do, or what we have to do, is to solve the Boltzmann equation for dark matter in this, if you want, non-standard background. So we have to solve the Boltzmann equation for the dark matter number density, coupled to the energy density of the inflaton and of radiation. And now, one technical note: this equation for the dark matter, let me reparameterize it in this way, where I'm using capital N to be the product of the dark matter number density times scale factor cube, and you can rewrite this expression in this form. It's better to do it in this way instead of the yield. And remember, the yield was the yield capital Y was the number density normalized by the entropy density. But here is not a good idea because the entropy is not a quantity conserved. So the yield, I mean, of course you can do it, but it makes much more sense to use this kind of parameterization. So a generalized yield, capital N, which is N number density times A cube. So if we do that, if we solve now the dark matter number density in this different background, so this is the evolution that you can find. So here I'm showing you the generalized yield, capital N, as a function of the scale factor A. So you can see that the dark matter is slowly populating, and the peak of the dark matter production happens at this moment where the temperature is basically T reheat. So you populate it very, very slowly. The peak happens when the temperature is T reheat, and then we reach a plateau. And for this, I'm taking a dark matter of 100 GeV, T max 10 to the 8, T reheat 10 to the 6 GeV, and an effective equation of state of the inflaton equal to 0. I'm also taking N equal 4. Remember, N is the temperature dependence of the annihilation cross-section that correspond, N equal to 4 correspond to operators, non-normalizable operators of dimension 7. So the peak of the dark matter production happens when temperature is of the order of T reheat, right? However, what happens if I increase the dimension of the operator, if I increase the value of N? So for instance, in this case, if I take N to be equal to 8, now you can see that the bulk of the dark matter production is not anymore at T reheat, but is much before that, right? So this for N equal to 8. And if I take N equal to 6, I will have like an intermediate regime where, okay, you can see that the bulk is not anymore, well, I mean, it's kind of balanced, right? So you have an important production of T reheat, but the production before that is not longer subdominant, right? So again, let me recap. So N equal to 4, you have the bulk happening at T reheat, much bigger values of N. They have that the bulk is happening at temperatures much higher than T reheat, closer to T max than T reheat, and this is an intermediate regime. So in order to understand what's happening, we can analytically solve the Boltzmann equation. So remember this set of three Boltzmann equations, and here I'm showing you the solution, the analytical solution, and you can see the dark matter yield, so the dark matter radic abundance that we are producing is having now a strong dependence on the value of T max, right? So a T max to a higher power that will depend on N. So the dependence, N, remember N is the temperature dependence of the annihilation cross section, but also to this critical value, so N critical, and N critical basically depends only on the equation of state. So if you take 0 for the equation of state of the inflaton after inflation, so this means that N critical is 6, right? So you will have a strong T max dependence if N is different than NC, and N is exactly the critical value. And we have a logarithmic enhancement, right? So log of T max over T reheat. Okay, so let me go back to the previous slide. So it's exactly the same plot, but now I'm putting the value of N compared to the value of critical value. So if we're taking omega to be 0, that means our N critical is 6. So if now in this case where N equals 4, so N is more than N critical, the bulk of the dark matter abundance is for temperature is T reheat. So as reheating, right? If N is equal to N critical, well, we have like an intermediate regime where this, okay, maybe the bulk of the dark matter is still happening at the reheat, but however, there's a contribution from temperatures higher than that. And if N is higher than the critical length, the critical exponent, the bulk is produced at much higher temperatures than T reheat. So more closer to T max than T reheat. And this is understood as term of these boost factors. So where the boost factor B is basically the ratio between the dark matter produced in the full full computation over the instantaneous decay approximation. So you can see that for N smaller than N critical, there's a boost of order 1. So basically the instantaneous reheat, the instantaneous reheat means the instantaneous decay of the inflaton with approximation. However, if you're in the critical exponent, you have a logarithmic boost, right? Logarithm of T max over T reheat. And if you're going to higher dependence on the temperature for this annihilation cross section, you have a very big boost factor of T max over T reheat at some big power, right? So this enhancement could be of several orders of magnitude. And here I'm showing you the boost factor in this plane N as a function of omega. So that don't take this too serious because, of course, these values of omega, I mean, I don't want to take any random values. And for instance, N can only take some discrete values, for instance, 0, 2, 4, 6, 8, blah, blah. Right? For instance, if the cross is if omega is 0, meaning if the inflaton, for instance, is oscillating in this quadratic potential, you can see that this boost factor could be of orders of magnitude. It could be 10, 10 to the 3, 10 to the 7, right? So there are big boost factors. Another thing I want to point out is that this boost factor depends, of course, on N and the value of omega, but also on the ratio T max over T reheat. Not on the individual values of T max and T reheat, but on the ratio. And it's also independent on the value of the dark matter mass and on the scale lambda of mu physics. Okay, so that's an important point, these boost factors. So now let's go one extra step forward, and it will be kind of an example of this non-oscillatory quintessential inflation. It's very simple, and you will see that things can change dramatically. So first, a couple of words about this quintessential inflation. So, so we took for the inflaton, which now it's called the cosmon. So we can have that action of this cosmon field to have this form where U is a general potential. In this case, we'll take a non-oscillatory potential. So the evolution, of course, will depend on the specific details of this potential. However, there's a kind of universal evolution. So for instance, that we want that during inflation, of course, the equation of state of this guy is basically -1. Of course, it's inflation. So, but at some point it will, when the slow roll parameters, when the slow roll is broken, we'll have an era just after the inflation of kination, right? So it's accelerating this field. Now, the equation of state tends to be equal to 1. And during this kination epoch, the energy density of the cosmon, of the inflaton, if you want, it's getting diluted very fast. It goes like 1 power 6. That means it's getting diluted very fast, much faster than radiation, and eventually we'll have the onset of the radiation domination, right? Because the radiation goes like 1 over the 6 factor over 4. And that's very, very universal, kind of independent on the small details of the choice for the potential of this cosmon, right? That's for the inflationary evolution. Now, what about the heating? So again, this will also depend on the details of the reheating, but there's some kind of universal trend that we can highlight. For instance, will take place during a very short period of time at the very onset of the kination era. That's one thing. And also it can be parameterized by these heating efficiency parameters, capital theta, which is basically the ratio of the radiation energy density over the cosmon energy density at the moment of the onset of kination, right? Where the kination period starts to dominate. So this one parameter, so the heating efficiency parameter, and also the Hubble scale, H king. And with these two parameters, we can, I mean, all the dynamics that is interesting for us can be parameterized. For instance, Tmax and T-reheat, that will depend on these two parameters, capital theta, the heating efficiency parameter, and H king, which is the Hubble scale at the onset of the kination period. So with this, we can compute again the dark matter abundance, meaning solving the Boltzmann equation for the background and for dark matter. And this is basically what we have. So I'm showing here a couple of plots of the scale lambda needed in order to reproduce the dark matter relic abundance as a function of the dark matter mass, right? And here, okay, and for different values of n, which remember is the temperature dependence of this annihilation cross section, right? And here I'm showing the analytical solutions for the Boltzmann equation in this kination background. So you can see again that there's a strong dependence on Tmax, right? And here I'm showing you the boost factor. Again, the boost factor is defined of the ratio of the yield, dark matter yield, in the complete the complete solution normalized by the solution in the case where we're assuming a sudden decay of the inflaton. And here again, you can see that the boost factor has a strong dependence on Tmax, and we have a boost that depends on the ratio Tmax of the reheat at a high power that depends on n over n critical. And in the case of kination, this omega is 1, that means that n critical is 0. So we have a boost factor that could be of several orders of magnitude. Okay, so that's what they told you. So kination corresponds to omega equal to 1. That means that the n critical is 0. That means that UV freezing is always boosted for every single operator connecting the two sectors. So we will have a boost factor that could be very high and will depend on this ratio T max over T reheat at power n, where n is the temperature dependence on this operator, right? And I think that was basically all that I wanted to tell you. So this leads me to my conclusions. So let me first recap a bit. So UV freezing is a completely viable dark matter production mechanism. And we have seen that in the UV freezing case, there's a strong dependence on the dynamics of the highest temperatures of the universe, meaning the reheating temperature even before that. So in that case, the instantaneous reheating may not be a good approximation. And in particular, it miserably fails when n is higher than n critical. And remember that this n is just the temperature dependence on this operator, so sigma b, which is basically the annihilation rate of standard model particles into dark matter particles, right? So we have defined these boost factors, B, which is basically the dark matter yield normalized by the dark matter yield in the case of sudden decay approximation of the inflaton. So if n, and here is more than this critical value of the exponent, and of course this critical value will depend on the details of the physics before reheating. So if n is more than n critical, there's a small boost factor, order 1. That means that the approximation of the sudden decay of the inflaton works pretty well. However, if the case where n is equal to n critical, the boost factors start to be important. In particular, it will logarithmically depend on the ratio of T max over T reheating. And if n is higher than n critical, there's a big boost factor that could be of the order of several orders of magnitude, and it will and you scale like T max over T reheat power n minus n c. That means that if n is bigger than this critical exponent, the bulk of the dark matter production happens near T reheating, sorry, near T max and not T reheating, right? And so these big boost factors are due to the non-sudden decay of the inflaton. And in this case, with T max, we can deduct the maximal, we can have temperatures much higher than the naive value of T reheat, right? That will depend on the effective equation of state of the early universe, right? So we can maximize this boost factor for steeper values of the equation of state. So if the equation of state is higher than 1/3. Also, we can, another way of enhancing this boost factor is having no entropy injection. So if the inflaton is not decaying into standard model radiation, because that means that we have no dilution. And that's exactly what happened in the previous case that I showed you before, right? So in this case, in the quintessential inflation, so we have no decay of the cosmon of inflaton into dark matter into standard model degrees of freedom. So we are not diluting the dark matter. And there are some comments I want to do as well, is that if now that we are taking kind of seriously this reheating process, I want to emphasize that there are some processes that we have to be taken into account. For instance, parametric resonance, turbulence, fragmentation. This is very complicated in general, but however, in the scenarios I showed you before, where you have a these non-oscillatory scenarios, these nonlinear processes are absent. So for instance, we take into account power law potential for reheating. So we have to be very careful because you have to take all these processes into account. However, in the scenario that I showed you just before, they're absent. Also, another nice feature of this scenario that I showed you previously, so what you have within non-oscillatory scenarios with kination is that the critical exponent is exactly 0. That means that the UV freezing is always enhanced, right? Because, right, if this operator is non-renormalizable, that means that n has to be at least 0. So at least you will have a logarithmic enhancement of the reheating. So that means that in this kind of scenario, the naive computation of the dark matter abundance using the instantaneous decay of the inflaton will fail. So you have to take into account the full production before reheating. And okay, that's basically all that I wanted to tell you guys. So I stop. Okay, that's all. Thank you very much.